I'm Christine Sumage, and I am with Andy Rader. We are applications engineer from Microchip Technology Incorporated. So, Andy, what are you going to show us today?
So today we will have a closer look at field programmable PWM controllers. This field programmable PWM controllers have been developed particularly for switchable power supply applications. The devices you usually use to design switchable power supplies are analog circuitries, integrated circuits dedicated for certain topologies and also for certain applications. The field programmable versions are giving you a hardware platform that can be configured during runtime and allowing you to tailor the internal circuit of PWM controllers to your very specific application needs. So let's have a look at how this looks like. So when we look into the world of switchable power supply controllers, the majority is pure analog circuits. So highly integrated circuits for dedicated topologies, power levels, and applications. So there are devices with integrated MOSFET drivers, auxiliary power supplies, which we usually refer to as switching regulators. And there are more discrete versions, which we call PWM controllers. PWM controllers in general allow you to better scale the controller to your application needs. So you can pick external MOSFET drivers and can design over a wider range of power and voltages. When we are, let's say, in recent years, application requirements are steadily increasing. So one new technology which is around for the last decade is the full digital control domain. So in these controllers, there are almost no analog circuits anymore. Everything is done in digital using ADC converters, DSP cores, and this technology is targeting high-end applications. Usually every platform that requires nonlinear control capabilities or also has to consist of sophisticated topologies with very sophisticated switching schemes. So now when we're looking at these two technologies, then these mark two ends of a spectrum. The so-called hybrid power devices are now introducing a middle piece, taking the best of both worlds and put it in one single device. And that is the kind of products we are looking at. So when we are looking into typical PWM controller architectures, then you usually find circuits like this. So there's always an error amplifier at the input, there are comparators, there are additional operational amplifiers for signal conditioning, there are PWM modules, slope compensation ramp generators, zero cross detectors, and usually there's additional protection circuits. So when we look into these quite complex circuits, then it would be then you will see that the interconnects between every single component is dedicated and fixed in hardware. So what we do with field programmable PWM controllers is, by adding a microcontroller, we can now alter these circuits. So basically we have now a device which allows us to modify the interconnects between different components, and at the same time we can, during runtime, measure and control and monitor every single one of them. So this additional flexibility now allows us to build block sets. Usually you get a set of operational amplifiers, which can be used for signal conditioning or as simple error amplifier. There are DAC modules, which allow you to program thresholds. Then you have comparators with enhanced hysteresis and filtering support for protection. There are ramp generators, PWM modules, standard PWM modules, and advanced multi-phase PWM modules, as well as zero cross detection, glue logic, and signal modulators. All of these components are merged in what we call a PWM controller peripheral block. So, and then the microcontroller is used to put them together, wire them up, and control and monitor them during runtime. When we look into the available devices of the PIC16F, 17.6X, and 7X family, then we find devices for single channel, dual channel, triple channel, and quadruple channel. Although we have defined certain PWM controller blocks, this does not mean that they are strictly encapsulated in one of these PWM controller blocks. So these devices still allow us to use components from another PWM controller for more sophisticated applications. So one example would be that we take one PWM controller block to establish an outer voltage loop and an inner average current loop, and then we take a second compensator to incorporate a second phase. So this assembly you see here is a control system for a two-phase interleaved topology. But it's not only about, let's say, smaller, non-isolated topologies. Also in larger scale, isolated offline applications, these devices give you a lot of the flexibility to design more sophisticated power supplies. So the example you see here is a quasi-resonant converter, flyback, which is operating as so-called transition mode flyback. So it means it incorporates the function of a PFC while converting the power from AC to a DC output. In this particular application, we would need a specific input interface which allows us to detect zero crossings of the AC voltage and use that rectified signal of the AC voltage as a reference for our inner current reference. So by having the flexibility in interconnecting multiple different modules, we can now establish a control loop which is perfectly tailored for this highly specific application. When we look into the basic architecture of one of the PWM controllers supported by the MCU core, then we can identify some standardized blocks. These blocks consist of a compensator, usually an air amplifier and a DAC, then modulators, which are defined by the control mode and the topology we're going to drive, and an additional fault level. So these three central building blocks will be reused in every application. The set of the three major fundamental blocks are then defining one PWM controller block. So the interconnect of various analog components can become very challenging, especially when you consider that you have up to 4 op-amps, 8 comparators, 8 DACs, and so forth, a lot of glue logic, and every single one of these blocks has various interconnect options, then things can become really cumbersome. So for that particular reason, we designed a tool chain which helps you to configure a power supply PWM controller with just a few mouse clicks. This so-called switchable power supply library is part of our MPLAB X IDE development environment, and it tries to follow the conceptual approach we have just seen on these chips. So the first and highest level is our topology level. So when you're starting from that level, then most of the interconnects already have been put in place for you. So eventually, you just need to give some high-level values like switching frequency, date times, clamping values, and then you can immediately generate the configuration which will put the PWM controller architecture in place for you. If you need to make some modifications, if you would like to use a different control mode, making modifications to the fault block or the modulator, then you get access to the second level, on which you will find the compensator, modulator, and fault block. These are still generic and pre-configured subsets, but you can now interchange or exchange multiple different versions of compensator, modulator, and fault blocks. If it's still not good enough, if you're still looking for a specific feature that your application may require, then you can go down to the third level, which gives you direct access to every single building block on these chips. And this gives you basically access to the last register bit to fine-tune, optimize, and optimize your system up to a level that you fully meet your application requirements. So, Tin, would you please show us where this SMPS libraries can be found and how we can get them installed on our computers?
Yeah, I'll show you. As mentioned by Andy, MCC SMPS Power Library allows quick and easy configuration and code generation for CIP hybrid power controllers like the PIC16F176X and the PIC16F177X device families. This library provides set of modules like for fundamental SMPS building blocks and can support up to 4 topologies. This library can be found in Microchip website. You can download this library and install it on the MPLAB IDE by following this instruction. First, go to Tools, Options, Plugins, then click on Install Library, then navigate to where the downloaded file is located. Click on the jar file and then install it. Once the library is successfully installed, you can now use the library under the MCC tool.
Thank you very much. So let's get started. We have prepared a couple of examples. So at the beginning, we will start with a very simple voltage mode controller implementation. Then we will change the modulator of that voltage mode controller against a modulator of a peak current mode controller. And then eventually we will add a specific feature by swapping the current feedback signal from a conventional current sense transformer to a DCR sensing circuit. So let's quickly look at the first example. So we're starting from a configuration of the microcontroller with a single PWM controller block. The board we're going to drive is our synchronous buck converter. This board is called the CIP Hybrid Power Starter Kit. It offers a synchronous buck converter, and the buck converter architecture has 3 different current sensing options. So it allows you to experiment with modifications of the switch node as well as different feedback signals. The controller used on this board is the PIC16F1779. So it's the 4-channel superset device. To support multiple control modes, we have utilized the various PWM controllers inside that chip. The first one we will use now is a compensator block which is pre-configured for voltage mode control. So it means the compensator consists of an air amplifier and an internal PWM module. So the only signals we need is a feedback signal from the output voltage, which is fed into the air amplifier. The air amplifier is then producing a reference voltage which is applied to an internal comparator. And the glue logic module of our PWM controller architecture then offers the SR latch and the clock inputs to generate a PWM output. The compensation network in this application is external. So as you can see below the compensator block, so between 2 pins, we have a RC network of a type 3 compensator which is stabilizing the power supply and which eventually gives us a certain bandwidth, performance and stability of our application. So, Tin, would you guide us through the process how we can get this configuration installed on our PWM controller?
Yes, of course. I can show you all how to configure and how easy it is to use the SMPS library to run this CIP hybrid starter kit in 3.3 volts output using the voltage mode control operation. To get started, let's go to the MPLAB IDE. Create a project that will work on PIC16F1779 and open the MCC. The first step in using the SMPS Power Controller library is to configure the system clock. In this example, we desire to get a 32 MHz clock frequency That's why we are setting the internal clock to 8 megahertz and enable the PLL. And then, since this configuration walkthrough, we were going to use a generic block in a topology level. Using the PWM block controller 2, let us select the sync block 2 by double-clicking it. On the configuration tab, you can easily change its operation to voltage mode control along with its high-level parameters, such as the switching frequency, maximum duty cycle, voltage reference for the error amplifier, leading edge blanking, the rising and falling edge dead times, and the sawtooth. When all the values for these parameters have been defined, click the Upload All. Basically, the parameters that you see here on the sync block 2 will let the CIP hybrid power controller to run in 3.3 volts output. Looking at the configuration again, the next step you need to do is set the pin manager on the sync block 2. In this configuration, the output PWM high is at port D5, and the output PWM low is at port D4. These pins should match on what we have on the hardware platform. You can also see here at the Pin Manager package view how the pins are mapped. After that, click on the Generate button so that the MCC will generate peripheral drivers and the SMPS library will be able to generate SMPS drivers. When this has been successfully generated, click on Program so that you can program the CIP Hybrid Starter Kit and evaluate its result. Andy, can you please evaluate the result of our CIP Hybrid Starter Kit?
Sure, no problem. So let's first have a short look what we are going to do to validate that our setup is working correctly and that our feedback loop is actually stable and the power supply is working as intended. So here we see a simplified schematic of our circuit. So on top there's the power supply, on the bottom there is our PWM controller configuration. So the device we're using is a vector network analyzer, which allows us to inject the signal and perform measurements. So this measurement is an invasive measurement. That means we need something to interface the vector network analyzer with our circuit. In this particular case of a loop measurement, we're adding a resistor on top of the voltage divider. This resistor needs to be very, very small in comparison to the resistors used for the voltage divider. Usually something in the range between 5 and 10 ohms. Across this resistor, we are now connecting a transformer, and it's a one-to-one current transformer. This transformer is connected here to the output of the network analyzer. So the frequency generator is driving a signal into the primary winding of this transformer, and the secondary winding is then pushing this out through our injection resistor. So the injection point now is connected to the circuit using these two clips. And then we are measuring the signals with two probes with our measurement input. So when we go back into the circuit, then we are now connecting the output to our transformer. And we also connect channel 1, which is the reference input, to the lower point of our injection resistor. So the reference is always taken at the high impedance side of this measurement loop. And now when we start the signal generator, we are injecting an error signal which is traveling through our compensation network area amplifier into our PWM stage. The PWM stage now starts to vary the duty cycle in accordance with the error signal we have injected, and that signal is then applied to our power plant, modulating the on time of the high side switch. This results in a generation of a sinusoidal waveform which is riding on top of our output voltage, and this frequency component is becoming visible on channel 2, which is used to measure gain and phase. So the difference in amplitude is then taken as gain, and the difference in phase gives us the phase lag of our power supply and control loop. The Bode analyzer now translates this into a Bode plot, and the Bode plot allows us to perform stability analysis, so we can have a look at the bandwidth, the stability, and the phase margin, high frequency rejection, and a couple of more options are available now when analyzing these measurement results. So let's have a look at the current results of our voltage mode implementation. So here, this is the software of our vector network analyzer. So when we perform a measurement, so it's continuously measuring the plant, and as you see, it is a so-called second order system where we have here pretty much in the middle of our plot we find this funny bump, and this bump indicates the resonant frequency of our LC network of the power plant. At this so-called complex conjugate pole, which is introduced by an inductive and a capacitive LC tank, the phase starts to drop by expected 180 degrees. Further up, we find another point where the gain is starting to shallow out, and that is called a zero, and that zero indicates is injected by the output capacitor and its ESR. So now the purpose of our feedback loop is to stabilize the system. So the compensator compensates for poles and zeros in the power plant. So we have to compensate every pole with a zero in our compensator, and we compensate every zero of the power plant with a pole in our compensator. The final outcome is now that we get a control system or an so-called overall system open loop gain, which falls steadily with minus 20 dB per decade gain slope. Then there comes the resonant point, and unfortunately in voltage loop there's very little we can do about it, so we need to work around it. The only thing we have to do is to make sure that this resonant bump is always in a positive gain region, and that the gain drop after the resonant point crosses the 0 dB line with a slope of as exactly as possible with minus 20 dB per decade. At the crossover point, we then go up onto the phase line, and we find our so-called phase margin. This is one of the most central parameters defining the stability of our power supply, and also has a significant impact on how our step response will look like. To make this a real robust power supply, we also have to look at the so-called gain margin. The gain margin indicates how capable our power supply will be to reject high frequency noise, so that any high frequency disturbance in the system will not affect the output voltage. So we find this point at the point where the phase crosses 0 or minus 180 degrees, and at this point we're measuring the gain, which gives us a gain margin of roughly minus 17 dB. So looking at this plot, we find this is a very stable power supply with a bandwidth of close to 20 kilohertz, 70 degrees of phase margin, and minus 17 dB gain margin. So Tim, I would call this a school book voltage mode controller. And if I counted correctly, It took us just 7 mouse clicks and roughly 4 minutes to get it in place. Pretty amazing. But what if I would like to change the control mode, let's say to PCAR mode control?
Well, Andy, it is very easy to do that using the SMPS Power Library, and that we will cover in part 2.